Come on, YouTube. You can do it. Okay. All right. I think we're live. Hello. How's it going?
Good. How are you?
Good.
Thanks for inviting me.
Yeah. Hey, thank you so much for agreeing to come on.
Half my time is going to Mars 2020 Perseverance operation. But now the Mars is behind the sun, so we have a bit of rest time. Because we cannot talk to the rover right now. The other half is spent for a bunch of research projects.
Yeah.
And one of them is, I believe, today's main topic, which is
Yes.
the robot to get into the crevasse of Enceladus, this small, tiny Saturnian moon, to potentially find life there.
Yeah. Well, we'll talk about that in a second. But you're working with Perseverance. I definitely have to at least talk a little bit. So
Of course,
So
of
what
course.
so what role do you have with the Perseverance rover?
I have and had multiple roles. I am an autonomy researcher. So I wrote the flight software as a part of the team for the autonomous driving because
Yeah.
we upgraded the self-driving capability compared to Curiosity. That was my biggest job, I guess. And also I was involved in the landing site selection. And now I am in charge of the mobility downlink. So basically, when rover drives, checking the status, checking the data to make sure that the rover is healthy, if it is okay to keep driving.
One of the big upgrades from Curiosity with Perseverance was that it fine-tuned its own landing, right? When it was coming into the atmosphere, it was looking at the ground and it was finding the safest spot to be able to touch down. So did you work on that as well?
I didn't,
No,
but it's
okay, all right.
sort of a related. So it's called the terrain relative navigation, meaning that the Curiosity was basically a golf. You hit a golf ball
Yeah.
and it lands blindly, right? But now, this tiny golf ball has its own camera looking down and recognize where it's going to, and where if it's going to a bad place, it applies a divert maneuver to land on a safe place. And to enable that, it needed a new onboard computer, what we call VCE, but it's a FPGA, much faster
Hmm.
processor for the images. Now it's landed, and we have this good vision processor that we don't use. Now we use that for driving as well.
Right. Okay. And so what impact has this level of autonomy provided in operating the rover? Has it made a big change? Do you feel it?
It does. It does. For example, the record distance per soul, the Martian day of autonomous driving was, I forgot the number, but about 100 meters. And we are still like soul 225. Our record is, I think, 170 meters or something,
Hmm. So almost
right?
double.
Yeah, and actually we can do more. So it's gonna be much more efficient. We can go faster and farther. So it's a great change. And actually, without this upgrade, we might not have been able to achieve the mission goals. It's a really challenging mission.
It's interesting as well, like with Ingenuity flying around, and I mean, this is all still just experiments, but you can imagine this future where every future rover to Mars is equipped with a helicopter. The helicopter flies forward, scouts all the terrain out to the maximum driving distance of the rover, and then returns back to the rover. And then the next day, the rover knows every tiny rock in the way and is able to make huge ground to get to the
Sure.
really interesting landmarks.
Actually, we do use helicopter in that way. Uh, a little bit. For example, the place where the rover is sleeping right now is called Sita, and that's one of the oldest and deepest unit in the Jezero crater where the rover is. We know that it's very sandy, it's very dangerous.
Hmm.
But we want to get in there because, as I said, all this unit, right? The scientists going to be very happy about it. So we flew the helicopter on the place where we thought the easiest place for rover, and took the photos from heli first before getting in there. So, initially heli was conceived as a tech demo just for 30 days, but now it's going much beyond our expectations. It's supporting, partially our rover ops and perhaps science a little bit.
Yeah, I understand it's not your decision to make, but do you see like these helicopters flying with every mission from, like, it feels like just an outrageous success to have this.
I agree.
Scout.
I agree. Again, I'm not in the place of deciding, but yeah, I personally would love to have this kind of a little companion, helis. Yeah.
Yeah, it's terrific. All right, so let's shift gears then and talk about the Enceladus Vent Explorer, and
sure.
And so, I've brought on people who have won NIAC awards in the past. So just, just to make sure that everyone is totally aware of this, this is a speculative project. This is purely an investigation. It's an idea of an idea. So we're definitely not into an actual confirmation from NASA that a mission is going to happen. But my hope is at the end of this interview, you will get an announcement from NASA that it's been greenlit and we're going to be flying. So that is the job. That's our job today. So let's talk about, like, where did this idea come from on trying to send some way to explore Enceladus?
Good question. Where did the idea come from? So there has been, I think it's more than 5 years ago, there has been this growing interest in IC wars in general among JPL, among NASA.
Yep.
And of course, ultimately, we want to get to that subsurface ocean where, we can find extant life. And around that time, most of us were talking about flying through the plume to get the particles, landing on it. We had a chat with a few folks. I am originally, as I said, the autonomy researchers, right? So I am, looking around and looking for challenging and interesting problems, right? And I talked to a few people. I think that was a meeting with Kevin Hand, who is leading, the IC world. You know him.
Yep.
So I think it was him who said, can you just send the autonomous robot down through the vent? And we were like, oh yeah, that sounds crazy, but maybe we can. And that kind of thing is a perfect topic for NIAC, right?
Yeah.
It's very challenging, but super revolutionizing everything. Yeah. And we don't know yet if it is possible or not, but the point of the NIAC is first to understand if it's ever possible.
Well, and it comes at a good time, I think. Like, DARPA just has had a series of challenges where they're sending autonomous robots into various underground caverns and urban environments and caves, and the European Space Agency is doing a lot of work in exploring lava tubes and caves, and so I think there's a lot of interest, and of course there's the work happening with NASA and even the Chinese Space Agency trying to figure out how can we explore some of the permanently darkened craters on the moon. So I think this sort of brings together all of the hardest parts of all of those problems into one special, really difficult problem, right?
And actually, you mentioned the DARPA subterranean challenges. JPL team, they just finished the competition, I think 2 or 3 weeks ago, and JPL team did a great job, and many of the members are closely working together on this subject, because we have a common challenges. We are exploring somewhere unknown, and and Sub-T was a great place to develop a mature the robotic, autonomy technologies in this direction. So, yeah, you're absolutely right.
Yeah. So then let's talk about the challenges then, and what it's going to be. I mean, all of the viewers, listeners at this point, we're all very familiar with this idea that Enceladus, these icy worlds, they've got geysers, that there's possible life underneath the ice on these worlds. So what are the unique challenges that you're attempting to overcome in being able to explore these vents? What's the
Sure.
environment? Send me the landscape that you're going to send this poor robot into.
So, let's start with what this moon Enceladus look like.
Yeah, yeah.
It's the diameter is about 500 kilometers, I believe, or 300 miles. So something like Texas, I guess. And I don't know exactly how big Texas is, and the gravity is 0.01 g, 1% of gravity. So it's basically, it's not zero gravity, but it's, gravity is it's more like an asteroid rather than our own moon. The surface is covered completely by ice, the H2O ice. The thickness could be 10 kilometers, 10 miles or so. And below that, there is most likely there is this liquid ocean, and that's our ultimate target. And what's special about Enceladus is, your background is exactly what I was going to explain. There are 4 crevasses running through the south polar regions of that moon, and through the crack, this hypersonic jet is blowing up to the space, and actually that water particle is the source of the E-ring of the Saturn. And so the challenge is the many. So you land on it, right? And it's likely that this ejected, ice particles are falling. So some of them are falling down back on Enceladus, and since gravity is so low, it's not like a ski mountain where the snow is nicely compacted. It's more likely super fluffy, a surface. So how to drive on it? The conventional rover is unlikely work on this fluffy surface. Once you get there, this hypersonic jet is another thing, because the upward force that you receive from the jet is likely stronger than this weak gravity. So, no worries. So you have to find a way to attach yourself to the ice wall so that you do not blown up to space and part of the E-ring. And also, unlike Mars rovers that I am working on, right? On Mars surface, we have these orbiters which can take 25 centimeter resolution images beforehand, so we can plan everything on Earth, right? But you are basically going into the unknown. No orbital reconnaissance, no knowledge whatsoever. So software-wise, it's more challenging, because you don't have any maps or any images, and you go there and learn about the environment and adapt to the environment. So all of these are very different from our previous missions, and that's what we are working on for.
And so
for the
often
project.
one of the early steps in this process is to search for some kind of analog, a place on Earth that is kind of the same. And obviously you can't get 1% gravity, although perhaps you could simulate that in some way with rubber bands attached to your rover. But is there a place on Earth that would feel kind of similar to the surface of Enceladus, do you think?
Yes. So one place that we are looking at on a parallel project, by the way, there are 2 tasks are going on right now. One is this NIAC. The other is the JPL funded task. PI is someone else, and I am the autonomy lead. On that task, we are likely going to Athabasca Glacier in Canada. And on the glacier, there is a vertical hole called moline. Maybe my pronunciation is not good. A vertical hole created by a water flow. And that at least is a geometric analog to the Enceladus vent. At least in our idea. Of course, we cannot simulate 0.01 g gravity or hypersonic jet, but in fact, this hypersonic upward jet, the force from it can be simulated by the downward force of gravity on Earth. So going down,
so you could like just do it in backwards, and
exactly.
It's interesting. It's sort of like when you test the parachutes for the rovers, you test them at really high altitudes at really high speeds here on Earth, and you can match the conditions of what it would be like to arrive on Mars. Maybe you can sort of create a similar environment. That's really clever. I like it. So I'm imagining. So you send this rover, and what do you anticipate that it's going to look like at this point? What are you thinking? Like some kind of spider, some kind of ice skater? Some sort
no one knows, right?
Yeah, something with like ice hooks. What's it going to look like?
Oh, you mean you're thinking about
the actual rover, the actual explorer,
the robot? So that's what we are going to find out on the NIAC project. We are looking at a few different options. Back in phase 1, we looked at a robot with limbs, where this ice screw that is used by mountaineers when climbing on the ice wall. We are looking at another architecture, for example, a snake-like robot, which we called eels, and they're gonna basically push the two walls to stick itself. We are looking at the octopus-like robot. Again, it uses its legs to push the both sides of the walls. There is one biggest remaining uncertainty is the size of the vent as well as the strength of this jet, because since we approximately know the flow rate, if the vent happen to be very wide, the flow going to be much weaker. So there could be a case where the gravity is actually stronger than the pressure from the flow. In such a case, perhaps you can hang a very heavy, kind of pendulum made of tungsten or something down to the ocean, and that could be an easier case. We also have an idea of an inverted rocket, that's going to be fun. So we'll see, what the architecture. But as for this Athabasca experiment, we are now building this snake robot, eels robot, to be tested.
I mean, it really sounds like you don't even know what you don't know yet. That the first step has got to be how do if these vents are very narrow, then that requires one kind of robot, and if these vents are 50 meters across, then that requires a much different robot.
Exactly.
And somewhere in between will require some other robot as well. And so you don't even have that data. So have you suggested a way to even map out the terrain?
So that's a very good question, actually. And in our NIAC, we are doing two things together. One is to know how to know about it. And that involves, scientists listing out all the parameters that we have to identify and how we can observe and identify, those parameters. And basically, it could be an orbital precursor mission before the Eve mission. So that's number one, to know how to know. The second is to identify the options for various possibilities. In one in the most optimistic case where the vent is wide open, you can just drop something or hang something from the top. In the intermediate case where the vent is, say a meter wide or so, intermediate width, where the robot can go in, but you need an anchor. The most extreme case, although our scientists speculate that it's unlikely, but say the vent is 1 centimeter, less than one inch wide, but in that case, it's unable to go down, but the jet can be stronger, meaning that splashing out more materials outside. So in that case, it's likely that we can get more information without getting in there.
What, I guess, there have been proposals to send, I mean, even like the Europa Clipper is going to be doing some observations of the vents that are coming out of Europa, maybe attempt to taste the geysers to see if there's any hints of life in them. Obviously, a similar mission at Enceladus would be very exciting to taste the geysers. And at the same time, you could probably also have a nice LiDAR on board at the same time that maybe you can do both. You can do like a really close flyby while you're flying through the geyser, also try to map out the tiger stripes and see what they're in. But can you get enough information from a flyby, or is there just something really special about sticking on the vent and tasting the geyser material?
Yeah, I like your analogy of tasting, but that's very appropriate actually. What we want to do is to taste is basically sensing the trace chemicals in water, and that's exactly one of the things that we should do to eventually find life. And there are, so by flying through the plume, there are things that we can do. You can obviously taste the ocean water, but the thing is that a bigger particle is accelerated to a lower speed and less likely to go up to the orbital altitude. So the sample is biased there. You cannot get the genuine sample of the ocean water up there. On the surface, it's closer, right? But still, it is limited to the particle that is, I think, the lower end in the size that is able to make it out there, and also whether the complex organic materials, or even a cell, or even if there's a fish, I don't know if there is, in one piece, if it is blown up to space or on the surface. That's another question. So ultimately, if you want to get the purest sample of the ocean, the best place to get the sample is in the ocean.
I imagine, I'm sort of envisioning, like, if you had an entomologist, like an insect researcher, and the only way that they could learn about insects is what hits their windshield as they're driving down the highway. They'd much prefer to be able to walk around in the forest and actually
exactly
look at bugs up close, as opposed to scraping the bugs that hit their windshield. So do you envision it as being its own, so like this follow-on mission, so after we've got some kind of understanding of what the terrain is looking like, whether you need an ice climber or a snake or something that just clogs up one of these vents, what does the mission look like? Like, what do you sort of see as sort of all of the parts that will come together to actually do this mission?
So, first disclaimer, we are still working on the column ops in the NIAC study, but but I can tell what it will likely, look like. So you land at least a few hundred meters from the vent, because obviously it's hard to land on top of it, and you traverse on this fluffy surface in some way or another. The robot is going to be tethered, likely, because for communication and power, you go down there, that could be slow, perhaps as slow as the Mars rover, which is a few centimeters per second. But unlike Mars rover, it should keep going down, because stopping there is not safe or energy saving anyway. So you keep going down. So it's gonna take a week or two, maybe more time. We don't know yet, but to ultimately go through this 10-kilometer-ish thick ice shell. Once you go there, you sample the water. And here's another trade. If we can miniaturize all the instruments so that we can put everything on this small, rover, that's small robot that's going down, we're going to do in situ analysis. Otherwise, perhaps some instruments like a mass spectrometer might not be able to fit within this robot going down the vent. Then maybe the robot has to go up again to deliver the sample to the lander. Or the tether has a small tube and shoot up the sample. There could be different ideas.
Right. So like the rover won't have necessarily all of the instruments on board to be able to fully analyze the samples that it's taking.
That's right. Accommodation is
right, but that would be, that would be the ideal, is that it's able to sample at different depths as it continues down into the vent.
Right.
As opposed to necessarily grabbing one sample and then bringing it back up and delivering it. But perhaps you could do multiple versions of that. So then I sort of, in addition to all of the terrain challenges and the size of the vent challenge, I sort of see some other challenges. One being power. Being out at Saturn, solar is off the table. So how do you anticipate being able to keep the whole thing powered in such an extreme environment?
Yeah, that's another great question. Solar could be an option, actually, because these days the solar cell is much improved than before. So, hypothetically, if we land on the summer in the southern hemisphere, and if you place the lander on the top of the Tiger Stripe, maybe, you might be able to deploy a huge solar panel. But of course, that's going to be much more constrained than have many challenges. Perhaps more straightforward way is RTG, might be. But that's another trade that we are working on right
now. Have you considered using the flow of the vent itself as a power source?
Oh, interesting question. Question. Actually, yeah. Thanks for idea. I have to put your name on the paper,
sure,
I guess. Well,
it's funny. So, like here in Canada, one of the options, like if you don't have power on your property, you can make a small hydro site. So you take a little stream that's running through your property, you put a little top vent on it, and then a pipe that goes down low, and then you have an impeller inside of it, and you're generating
really?
electricity for your house. Yeah, and there's a bunch of these options, and so I wonder if that the pressure coming out of the vent gets so strong that maybe you could use it as a power source.
So I think that depends on, again, what the vent would look like. If it is at the right size, not too small for a robot, but not too big so that the jet is weak. Yeah, that could be a great idea, actually. All right.
That one's for free.
I'll mention your name to NIAC.
Perfect. Yeah, well, yeah, that'd be great. Finally, that's the dream.
Yes.
So the power is one. And then, of course, the communication, the time lag to be able to communicate with Saturn is ridiculous. It is, you think talking to Mars is hard. Saturn is so much farther. So I'm assuming this is where all the autonomy comes in.
Yes and no. It's not too ridiculous. I think just a few hours, right, from Saturn. I don't have top of my head.
Yeah.
And on Mars, we only communicate. We do not communicate all the time. We only communicate a few times per day. So delay. So it's not. Yes. You're right that of course we cannot joystick with few hours delay. But beyond that, it's more about the level of unknowns, because on Mars, even though the data only comes few times per day and the operation cycle is once per sol. But as I said, you can look ahead by orbital images, or if you take a picture from the Mars rover, you can easily see 50 meters, 100 meters away from where you are. But in the vent, can you see 50 meters ahead, 100 meters ahead? No, you cannot. Perhaps you can only see just a meter ahead of you, 1 yard ahead of you. So that's the fundamental difference, in my opinion.
And actually that sort of led on to my next question, is just like the visibility. Like you've got very little light. You're now going down into one of these vents. It's going to be very, very dark.
Uh,
You've got potentially this spray of water vapor and other particles all
yeah.
around you. What kind of visibility would you be able to get? Would it be like in a steam room, or is it not as, not as bad?
I guess great question, Fraser. That's depend on the eruption mechanism. We are There are, super roughly speaking. I mean, there could be countless possibilities, but they're roughly speaking two very different possibilities. One is so-called boiling model. Basically, imagine this boiling pot. That's it, right? You have a smooth, nice surface from which the vapor is going. So in that case, it's predominantly gas or ice particle coming out of it. The opposite possibility is what we call cryovolcanic model. It's basically volcano, because the ocean water, we know that the Enceladus ocean water contains gas, and as you move up, the gas dissolved in the liquid comes out as a gas, inflates, and that gonna pushes the water up. Imagine you shake the Coke can and open it. It's basically it. So in such a case, yeah, it's a splashing Coke can basically. The water and gas are mixed together and go up. So there's no clear water gas interface. In such a case, it's mixture of gas, liquid, and likely solid as well is going up. That could be a more difficult situation. So again, system, what kind of perception system gonna likely work most robustly? And what I'm imagining is that is a combination of different sensing modalities. And you go there with multiple sensors, and then you're gonna decide which one is most reliable.
I know that the payload of the scientific instrument payload is always a very tricky challenge,
Ah,
and I'm imagining the difficulty of packing sensors into a
yes.
snake or something very small. What kinds of instruments would you love to be able to have on board the
Mm.
rover as it's crawling down?
There are obviously many kinds of sensors that we want. Speaking about the life detection, that obviously one of our main goals. There are chemical observations. There are physical, optical. As Carl Sagan famously said, the extraordinary claims require extraordinary evidences, right? So you have to collect a multitude of evidences to so that your hypothesis of life is not shaved away from Occam's razor, right? So you need chemical evidences, which means detecting the organic molecules and perhaps DNA or something, if it is life as we know. If it is a cell or even greater, thing, microscopic imaging of the thing that maybe life could be one. So it's going to be a combinations of many kinds of it. And by the way, JPL is working on an instrument called OWLS that combines all these aspects and uses machine learning for detecting this moving cells. So that going to be also exciting.
How like, I guess, how bulky, how heavy, how power hungry are these
Good
kinds of
question.
experiments?
We don't know yet. We are looking at a huge set of instruments right now, and yeah. Again, we are in the middle of the trade study to understand, what can be accommodated to accommodate this set. How big it is. Can we scale the robot to that extent? I think like the difficulty of challenge of this trade study is everything is coupled, right? Um, from the payload to the launch vehicle. So yeah, we'll see.
Yeah,
In
yeah.
9 months from now, you're gonna have a much better. So yeah, you can ask me again.
But right. But I guess
In
it's
nine
sort of like
months.
this challenge. I mean, if you could have a microscope on the rover, if you could have a some way of sensing some teeny tiny mass spectrometer, as you say, this was it owl? Is that the name of the
Owls, yeah,
owls?
ocean
Yeah,
world.
right. It's
I
I
forgot.
think I've learned about this. Right, it's just like a generic life detection
Exactly.
system that can then
Suite
be a
of
suite. Yeah, that could then
yeah,
be applied. But of course, if you do have the lander sitting there, then if you are able to bring samples back up, then you can deliver them to the lander, and then it
exactly.
can it can crunch them and figure out what's going on, and I guess that's again the challenge. So I mean, it was Europa that sort of brought this idea in the beginning that you could have these vents that are a way to access this underwater ocean. Places like Titan are maybe even more fascinating, and also at Saturn, where you've got this hydrocarbon atmosphere, you've got methane lakes, you've got ice surface, and then a subsurface ocean. Do you think if do Europa or Titan make more compelling places to go than Enceladus, or would Enceladus still be your top choice based on what you know right now?
Yeah, that's a great question. I mean, of course, I'm not a scientist, so I cannot say with confidence. But yeah, personally, all of these places have different possibilities and potentials, right, for finding life. The reason that we are focusing on ancestors, at least for now, is because the gate is open. We know that the gate is open on Titan. Maybe there are some observations suggesting that there are going to be a plume on Europa, but that's not directly observed. As opposed to Enceladus, we know that this jet is there, which means that there is a pathway open for us to get to this ocean, right? So it's more about engineering challenges. How to go through this super thick ice shell to get down there, and Enceladus seems to be, at least as far as we know, the closest body to get into this subsurface ocean. Gate is open.
Right,
That's the
right,
key.
right. So if a similar system is found on Europa, or if something similar is found on Titan, then options definitely expand.
Of course, and I'm gonna
Yeah,
be super excited.
yeah. Well,
Yeah.
I mean, it's really interesting that the thinking seems to be at this point that these icy worlds are across the solar system. That
Uh,
that that not just Europa and Enceladus, but maybe Pluto, maybe some of the asteroids, some of the cosmos
yeah.
objects. Who
Yeah.
knows what's out there? Like, and the problem is that it's locked behind this icy shell, and so it's a really tricky place. Life could be everywhere. We just can't see it because it's so hard to get at.
Even on Mars, there's this polar ice caps that has, that draws
Oh
substantial
yeah,
interest from
yeah.
scientists. Uh, 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 Not about, I don't know about, the extant life question, if that's a good place, but maybe no one knows, right? Yeah.
It's interesting. So once this technology can be figured out, I mean, the polar ice caps on Mars, they actually sound like an ideal place to test out a lot of this technology. I mean, you're probably
Yeah.
not going to find geysers necessarily, but you're going to have a very similar environment to explore and
Uh-huh.
study. I mean, it's it feels like it's funny. Like we've gone from this time of orbit or flybys, and then we've moved to orbiters, and then we've gone to landers, and then we've gone to rovers. And they're still all very generic ideas. But the next step, I guess, is starting to come up with platforms to handle these very complicated environments that are also the most interesting. That, when you've got a lander sitting in the sand and all it can do is shovel around itself a meter and dig down half a meter, there's only so much you're going to be able to find. But once you can crawl around and move around and get down into it, I think it really changes everything. So it feels like,
Yeah. So that's a great way of viewing it. How we evolved our ability, and technology-wise, the history of going from flyby all the way to roving and drilling and getting subsurface. That's about dealing with more direct contact with the body that we are sitting, right? In flyby or orbiter, the only interaction with the body is gravity, and it's well known. It's very smooth. Therefore, it's the easiest. Once you land on it, you're going to be direct contact with the surface, which is highly unknown. So that's another level. If you drive on it, you're going to encounter more unknown. So that's one level up. And if you drill on it, that's even another level up, right? Because you have a deep interaction with this physical interaction with the rock, and you saw that we unexpectedly failed the first attempt of the drilling on Mars, and that exemplified how hard it is to in terms of the technology to interact with physically interact with unknowns. And now we're trying to bring it to yet another level, which is going subsurface. So you have to have the physical interaction with the body in many ways. But that's the way that we have been advancing our technologies over decades, and that's the key that as you enable more physical interaction with the body, that directly means more direct observations for science, right? Yeah, so that's where the technology is going forward, and that's how technology is helping the science to know more about the bodies.
well, I mean, one of the most innovative groups working on this kind of thing is JAXA with the Hayabusa mission and
Oh yeah,
and the upcoming mission to Phobos.
yes,
You've got just this attachment of a whole bunch of just little rovers. Hayabusa 2 had a German rover, as well as it had a tank shell that it fired at the asteroid. And with the Phobos mission, they're going to be sending ideally some rover that's going to be able to go around the surface. And seeing what's happened with Ingenuity being attached to Perseverance, do you see a larger role for these additional smaller rovers, flyers, crawlers, snakes to come along with the mission?
Yeah, absolutely. And by the way, I am originally from Japan, so I have a lot of friends working on Hayabusa and NMR, and I am very excited. And yeah, and obviously, this samples coming back from the asteroid is and the Phobos sample is super exciting. Speaking about this, some payload, yeah, I mean that's important for many ways, right? One is for one thing, it supports multiple modalities of observation. Take an example of the Mars rover and Heli, and as I said, Heli is a great vehicle for scouting, right? And perhaps in the future it can do the science on its own. You have different viewpoints. That's one thing. For technology-wise, the sub payloads, because it's it can take more risk. You can test more advanced technologies. Let me give you an example. The Perseverance, its main CPU is still RAD 750, which is basically the PowerPC 750 in 1996 or something. Very slow. But helicopter actually has better computer, which is Qualcomm Snapdragon. The reason is that heli is a small class mission, so it can take more risk than the rover. So with that, you can test new technologies on Mars that could potentially be used for the class A mission in the future. So for advancing technologies, these sub-payload companion vehicles would be highly useful in my opinion.
Yeah, it really feels like that was one of the innovations. I mean, I really enjoy the JAXA missions just in general for the ingenuity and the willingness to experiment and try stuff that could be fairly risky. Like I find on the spectrum, NASA tries to be very safe, and JAXA is willing to take some very big risks, and sometimes it doesn't pay off. I mean, we saw what happened with Hayabusa 1, but
Right.
but Hayabusa 2 has been an incredible success, and I love the ambition of these sub payloads, and I think NASA is now really starting to experience that with Ingenuity attached to Perseverance,
Right.
that these sub payloads, because you can communicate with the main spacecraft, you've got a lot more flexibility in what these subcraft can be, and at the same time all the miniaturization and technology is unlocking this entirely new field, and so it feels to me like there'll be a lot more of this coming in the future.
Yeah, I guess my Japanese friends at JAXA are gonna be happy to hear that. But I think what I like about JAXA, particularly ISAS, which is a branch of JAXA, which is doing scientific exploration, they have a strong sense of rivalry against JPL NASA, but which is a healthy thing, right? Of course we do collaborate in many aspects, but they are not satisfied by a subscaled model of NASA. They are still aggressive in good sense. They always looking for opportunity to beat NASA, right? But seriously, but this kind of I think this is a healthy rivalry, right? Because in the end, if JAXA made a first, the asteroid sample return is one example, and and we made a lot of discoveries out of it, and that the discoveries in science gonna be shared a thing among humanity, right? Not about JAXA and NASA. So yeah, I think they are doing a great job.
Yeah, same with all of them. So then, like right now, was it a phase 1 award, or are you in the phase 2? I forget which.
We're in phase 2.
You're in phase 2. Okay, so what will phase 2, like what is the deliverable at the end of this phase of the study? What are you hoping to deliver into the hands of NIAC when you're done?
So in the end, we are delivering the roadmap, the technology roadmap. So after all of these trade studies and analysis about the event environment, what we need to invest in terms of technology and science, maybe, to make this mission come true, perhaps within a few decades. So that roadmap is going to be our a final product. But of course, we're going to deliver our result of the system trade study. So you will see a few point designs depending on the possibilities of the vent. Maybe this Eagle's robot, maybe this Lind robot, maybe this hanging from the top, and some model suite of instruments. So you will see more and more details towards the end.
And based on your understanding right now, I mean, Saturn is so far away. Like any mission, you've first got to imagine it's going to take you 5 years to just get there. Maybe faster if you go on something bigger, but it's a
I don't view
long
Saturn as
sprint.
far away because, compared to the scale of the universe,
It's oh, sure, yeah, of
yeah,
course. Don't
yeah, 10
yeah,
billion light years about the extent.
fine.
Saturn is
Yeah.
just a backyard, right?
Okay, all right. You're patient. Yeah, if
Yeah.
you're
But the
patient,
thing
it's
is
not that
this,
bad.
human civilization has just started, right? I don't know, just 10,000 years ago. And we are so immature yet.
Yeah.
So we started from, our backyard, and we are still in a backyard. And, we hope that, the life exists somewhere nearby, like Saturn, but we don't know. And this venture gonna, continue surely, much beyond my lifetime, right? It may take thousands or tens of thousands of years, beyond this point, and it's a long journey. We're gonna surely complete the exploration of the solar system, then go beyond. So yeah, but nonetheless, if it's a big if, but if uh, uh, maybe it's Mars 2020, maybe it's EOS. If this happens, it's gonna find the first evidence of the extraterrestrial life form. That discovery is gonna forever stick to the history, right, of science. No matter what, because it's basically Darwin or Newton moment, right? So I am so excited that it might happen in the next few decades, maybe in my lifetime, and I am even more excited that there's a chance that I might be a small part of that huge discovery of humanity, right? That gonna forever be remembered.
Yeah. So then, like, let's say that you finish the Phase 2 NIAC award, you then are awarded a Phase 3, maybe,
Ah,
or
well, we
um,
don't know. No one
who
knows.
knows? Who knows? And then then maybe it turns into a, you know, one of the next level programs, maybe one of the smaller ones, or maybe a larger one. What do you think is kind of a realistic timeline that you could like launch by, arrive at, and how long would you want to do your primary mission?
It's hard to say. It's really hard to say. Realistically, it's also influenced by community's interest, NASA's budget, etc. etc. So, but technically, technology-wise, uh, of course, that's something that we're gonna say in the roadmap. We believe we can make this technology ready by the end of 2030s, even earlier. Uh,
That's not so that's not so bad. That's like a little after maybe Dragonfly arrives
yeah,
at Titan.
yeah.
Yeah.
But of course, it's up to if we want to fund this program or not, because there are many other interesting things in the solar system and beyond. Um, yeah, and budget is limited, of course.
Yeah, yeah. So if people want to keep track of the program and what you're working on, where should they go?
So there's a NIAC webpage of this task. Google Enceladus Vent Explorer, and there will be more update from the other companion task, which is called EELS, EELS. I think if you Google EELS NASA or EELS JPL, there will be an excellent presentation on YouTube by our PI, Kaylin Carpenter, who is also a member of this NIAC task. So you can, and as we move on, I think we're going to have more news from both tasks. So please stay tuned.
Yeah, fantastic. Well, Hiro, thank you so much for taking the time to chat with me today. It's very exciting. I'm definitely rooting for you to eventually see this fly in our lifetime. And I mean, it's like there's probably no more exciting place in the entire solar system to look for life. I mean, there's water, there's hydrogen gas, there's energy. It's all there. We just need to somehow stick a robot, let a robot crawl down and see what it can find, and hopefully we can get that confirmation of what, as you say, a Newton moment. It's an Einstein moment. It's like possibly one of the most important discoveries in the history of humanity, that there is life somewhere other than Earth. and it would be
I
amazing.
fully agree, Fraser.
Yeah.
I appreciate it.
Yeah, awesome. Well,
Yeah,
again,
hopefully we're gonna make it happen.
sounds good. Let me know.
Let's see.
Let me know when you find it.
Yeah.
Thank you so much.
Yeah.
And
Thanks
good
so
luck
much.
with your research. Take care.
Thank you very much, Fraser.
Bye.
Thanks. Bye.